I studied electrical engineering at the TU Berlin, and like many of you, I was really fascinated of CPUs, right? So it's just amazing that you can take a little bit of dust, you merge it with some materials, and then you get a CPU working, right? So I've done a lot of physics stuff, CMOS circuit design. I also had the pleasure to look at these circuits through microscopes and design all of the stuff. However, then something happened. DeepMind published this paper, playing Atari games with neural networks. I think everybody knows this paper. And this is already 10 years ago. And during this time, I started working on some libraries like Gym. Do you know Gym? Who knows Gym? It's still used today. Nice, cool. So, and then AlphaGo, of course, yeah. So, which is a complete paradigm shift, because in electrical engineering, everything is deterministic, right? But now we have machines that can learn, understand, kinda, and reason, kinda. And yeah, that's why I joined the field. And I found out that a quite successful research lab is actually located right here next door in Berlin. And I applied as a Hiwi, stayed there for a PhD, and now I'm almost finished. So yeah, these folks are my team, and many of them actually contributed indirectly to this workshop. So let's start. So I think this will be quite interesting, because we will put ourselves into the shoes of a neuroscientist. So let's imagine you want to understand a human brain. And what would you do? You see these billions of neurons and you have no idea what's happening, right? It's just too much information. So what you can do is you can try to categorize specific parts of the human brain, like what is responsible for voice, the other one for linguistics, and so on. And we try today to do the same with a language model, the transformer. Who has experience with transformers? I would hope that every hand raises. Okay, if not, it will be fine. We will do a very short recap of the attention mechanism. Does everybody hear me, by the way? Clearly? Nice. Okay. So we will work with the Llama 3.21 billion model, and we will map out the entire architecture. I mean, a little bit, right? So we will ask ourselves questions like, which attention heads are responsible for in-context learning? Which heads are responsible for parametric knowledge retrieval? Can we use it somehow? Can we steer the model? So we will touch on a lot of stuff. And I think if you have no experience with explainable AI, this will be really interesting, because we go from 0 to hero. We will really start from the basics till state-of-the-art stuff. Okay, so let's not waste time talking a lot. So we will focus on these attention heads. Why? I mean, you know, there are also these MLP blocks, but we will ignore them for today. It's just too much information, and the most interesting part are actually these attention heads. So, quick recap. Everybody knows this formula, right? Which revolutionized everything. And you just need to know that we have these queries and keys, and they together form these attention weights, right? And then we have the values, which are transformed through another n and linear layer, and they form this attention output. You can open the Colab. There I have a very short demo of the attention mechanism. So, very, very briefly, in this view, we say that every single, so okay, just imagine every single key is in a database, okay? And now you'd like to retrieve the capital city of a country. So how does it look like? You have all of these key vectors in latent space. And now the transformer wants to know, what is the capital city of Germany? So it puts in some query, which encodes capital city, and this query will be compared to all keys. And the key, which is the nearest, will be selected, and then the value of the key will be selected, right? So the query can be anything. However, the keys are mostly fixed. I mean, for the same sequence. And if we go back, this type of attention happens in parallel for all inputs. And then you get this attention weight matrix. So on the left side, you have the queries, where each single query is independent from the other one, trying to find its pair, and then retrieving the value. So for instance, I don't know, this query here is highly interacting with this key, and then taking the value from this key and writing into this query. So the flow is to the left. Information from the right is taken and written into the left. This is important to remember. From the right to the left. That's it. Okay, so as neuroscientists, now we want to start understanding how a human brain works. So we need some sort of tools, right? So they use electrodes, microscopes. What can we use? We need some sort of algorithm to tell us which parts of the model are actually important for a specific prediction. So to see this, let's assume we have the following prompt. NASA's Calypso satellite measured 182 million tons of Sahara dust. But recent studies suggest it actually is 27 million tons. Now we ask the model, how much dust is blown out of the Sahara each year? So we know in the next step, the model answers the question, but it does not answer with one token, not two, but with an entire probability distribution. It could look like this. So the model aggregates all of this information in parallel, which means that this entire architecture is a completely massive parallel machine. So like a human brain, a lot of different neurons are firing in parallel, and there's a lot of chaos, right? We need some sort of tool to disentangle all of these different information flows. So intuitively, we know that this sentence is responsible for this prediction. And we know that this sentence is responsible for this prediction. And intuitively, the same also in the latent space. And if you would mask the name of the satellite, it would not affect the output of the model, right? It's completely irrelevant. So this tells us already there are some parts in the model, right? For instance, all of these attention heads, which process the name of the satellite, but they're completely irrelevant to the final prediction of the model. Likewise, if we mask this sentence, the probability will drop drastically. So this means that these tokens are really relevant for the prediction, but not for the other token prediction. Likewise, in the latent space, if we mask these tokens, it will drop. And what I've shown you is a technique called perturbation. So you have some input X, you perturb some parts of it, and then you observe if the function output of the model changes. And the impact it had on the change, or the change itself, it's defined as the relevance, the impact this feature has on the model prediction. Is this clear? Because this is really important to understand. Are there any questions? So if something is unclear, just ask. No worries. Okay, cool. Let's try to implement this and see what happens. Okay, so I hope everybody has set up the environment. Okay, we start with perturbation. We have nice. All right, so we already initialized the model, and we loaded in bfloat 16, which is just some numerical format, which allows us to compute gradients, because these models are trained in bfloat 16 or in float 32. But this is not so important to understand right now. All right, so we define now the prompt. And here we have an attribute function, which is performing this perturbation. It works the following way, that we first take the prompt, we tokenize it, and then we need some sort of baseline value. When we go back to the ablation, to the perturbation, we have to set the value x to some arbitrary baseline, right? To maybe 0 or some other value. And we choose now as baseline this underscore function. So what we're doing is we iterate through all of these tokens here and replace each token with an underscore. And then observe if the model prediction changes or not. And to do this, we extract here the ID of the token. And then we do a forward pass with the original input and take the logit outputs at the last token position, because there we have the last token, right? Which is the answer of the model. And then we take the baseline score, which is just the prediction of the model in the original case without any perturbations. And then we have this loop where we go through all of these tokens individually, and we have to replace them now with this underscore, and then compute the difference of the logit values. So I would like you to implement the small function here, just 5 minutes, if you can. Or if you don't have any Colab, just try to think about how you would do it. Okay, so the key is to so we initialized first this attribution variable with zeros, right? And then we have to fill it up again at the ith token position. To do this, we already have the base score, which is the original logit value of the model. So we already got the clone. We first clone the input IDs, right? Then we replace the token at position I with the underscore token. Okay. Then we do a forward pass, take the logits. Then at the last token position, at our target vocabulary entry, we take the value, and then we just compute the difference. Does it make sense? Okay, because that's important to understand. Would be if there are any questions, just ask.
Gotcha. So why do we have the 0 index in input IDs occluded, right? Why is there the 0? I did just the I and then...
Okay. Yeah, so the shape of the input IDs is batch size, comma, sequence length.
Okay.
So we because the batch size is 1.
Okay, and so we have batch, okay, gotcha.
Exactly.
Batch size 1, gotcha. Okay.
All right, cool. Any more questions? Yes? Hey, behind you.
Yeah. I have a question about the perturbation method itself.
Yeah.
Given that a word in natural language can correspond to multiple tokens, how would you identify the score for a word when it's composed of multiple tokens? A large word, for example, can be tokenized into multiple tokens.
True. Yeah, that's a good point.
So it does not need to be one token.
Yeah, so here we just do token level perturbation. We don't take the entire word. That's a good point.
But then you won't have a score for the entire word.
No.
All right.
Okay. I see.
Hey, sorry, one more question.
Yeah.
I guess it also depends on what you choose as the baseline token as well. Like,
exactly.
I just chose hash and then the color changed, of course, a little bit, not too much, but yeah.
You already computed the heat map?
Yeah, because just running
cool.
the function.
Nice.
Okay, I see.
Yeah, exactly. Yeah. So it depends on the baseline you choose, which is a problem. We might touch later on. Okay, so let's just run the code. And now we display a heat map, which is telling us how important a specific token was for the prediction of the model. So we have this function, right? Then we take our prompt again. Yeah, this is just for plotting here. We take the prompt, we decode it back to strings, and then we do a heat map in the Jupyter notebook. You don't have to understand this stuff, it's just for visualization. So if we do this, it's not defined. Ach so, yeah. So now it's iterating through all tokens, which takes some time. And then we get this. So this means token 100, this one, 182, is actually really important for the prediction of 182. What a surprise. But also how much, because without this much keyword, the model wouldn't know what to search for, right? So the question is also really important, which will pop up later on. So what is the problem with perturbation? So you can, again, just forget everything you just learned. Somehow with the, okay. So the problem is, so while it is used basically in all research papers right now, and it's the state-of-the-art method, it only works in very small toy settings. Why? Because you have to perturb each single token individually. Now, what happens if you also want to do this in the latent space, right? We also have 500 attention heads in a very small model. Bigger models might have 2000 attention heads. Now you have to perturb everything again. So it is 500 times 1000 perturbations for this small language model. You are already at 500,000 forward passes. So it would never compute. So this means we need some other way to get an attribution score. I promise this is the only math slides, and it's really easy to understand. I think so. So the idea is that we do a local approximation with the gradient. It works in the following way. So we have now the function f of x, right? Now we do a Taylor approximation at x itself, because this is our input x, and this is our anchor, where we do the linearization, some sort of tangent, right? So this looks like this. And now we perturb, so zk is our perturbation. And for a specific k, it's because we just changed one k, right? For a specific k, we set zk to some baseline. And in all other cases, zk is equal to xk, because z is an n-dimensional vector, and we just change which is equal to x, and we just changed one single entry. If you didn't understand it, it's not so important. At the end, you derive to this formula where you take the difference again, and you will see you can do the same stuff, just taking the gradient times the input, minus the baseline, which is crazy. It means you just do one single forward pass, one single backward pass, and you're done. You don't have to do 500,000 perturbations. So let's try it out.
Sorry.
Yeah.
Who wants to lead them?
Okay. Very briefly. So, you know Taylor approximations? Or
Well, yeah, somehow.
okay. Yeah. So just imagine you have the function f of x, and now you want to walk to one direction in the function space. So what could you do? You can take the gradient at x, and then you multiply it with the step size. You go into the gradient, and then you end up at z. So it's a little bit of math.
You need to know x.
Yeah.
So what was the specific question, right? Because I think it's hard to answer if it's not really clear what you need to know.
My problem is about the constraints, which are assumed by this.
Which constraints?
Basically, one is around a single point, and if the structure, the gradient landscape is complex.
Very good point. We will touch on this. Do we see? No, very good point. Okay, so let's do it now. Oh yeah, okay.
I mean, this is probably very obvious. Just confirming. So xi minus bi, that's of course on the in the embedding space, right? I mean, we're doing this, and then so xi minus bi, the one that you're doing, that's of course in the embedding space, and then we just multiply with the whatever the
the baseline can be anything. It could be also outside of training distribution. This is a problem. So you have to choose one baseline which makes sense for the model, right? I mean, if it's trained on cats and dogs, and then you put in some I don't know, elephants, that's completely confused, right?
I see.
Okay, let's just implement it very fast. Oh, sorry. Okay, sorry.
Could you maybe explain why it's important to make this linear by taking the first order approximation?
You don't have to do it linearly, but it's just very simple. You just take the gradient and the input, multiply it, you're done.
But in theory, you could use more terms in the series expansion, right?
I haven't done it before.
Would that not make it more accurate?
I mean, you have to compute the Hessian, right? If you want to take higher order terms. I haven't tried it yet. It could work. I'm not sure, yeah. Maybe here's the pro.
Just out of curiosity. Thanks.
Okay, so let's try. So the idea behind the linearization is, from my point of view, is that you take something highly nonlinear, very complex, and you approximate it linearly, so you have access to the individual components in this latent space and can investigate them individually. So this is at least my understanding of why you linearize at this point. Because if you go to higher degree Taylor approximations, then you have those interactions between those, in this case, latent dimensions again, which makes it hard to explain them individually.
All right, cool, thanks. Any more questions? Okay. Okay, the last one, then we have to move on, sorry.
Do you actually have some amplification on, because this sounds the same when people are talking out? It's for the recording. That's my only question.
Okay.
I have a question related to this. The last one I promise. So what we're doing is with the linear, with the Taylor approximation is just we say the higher the slope, the higher the relevance. As an intuition.
You can take this intuition, but it's not 100% the same, because you also multiplied with the input. So let's say you have a high gradient.
Yes.
But the input is 0, then you would get 0 relevance, right?
Okay.
Or let's say you have a negative gradient and a negative input, then it's suddenly positive.
Do you also
So it's actually the difference of the function. Actually, this is what we try to approximate.
So you basically approximate the model, and multiplication of the input helps us to approximate how the model interacts with the data and the changed data.
It takes both into account, the model weights and the data itself.
And the magnitude of the gradient is also important?
Sorry?
The magnitude of the gradient is also important, or just the direction of the gradient?
The magnitude, yeah, because it's in the formula, right? You take the gradient times the input. If the gradient has a high value, then also the relevance will have a high value.
We should give it back.
All right, let's move on. Okay, this is a function, attribute input times gradient. So we'd like to implement this very fast. I fear we don't have so much time. So let's just do it together. Okay, so we take the input. And now I have to use a trick. This is important. I cannot just compute the gradient on the input IDs because they're integers, and PyTorch does not allow us to compute gradients for integers. We have to convert them into floats or tensors. So to do this, we take the embedding layer of the model, which is done here, and then we put in the input IDs, which will give us input embeddings. And these embeddings are continuous, and the PyTorch autograd engine can actually compute these gradients. So Luckily, you can also just put in the input embeddings in the Hugging Face interface. You do a forward pass. And yet, now you just, again, take the logit value of the you'd like to explain. Oops. Oh yeah, Copilot is really nice. It's actually correct. Now you compute the backward path, which is also correct. And now you take the gradient at the input embeddings, right? Because that's the input to the model. So now we take the input times the gradient, and that's it. So we transform it back to float, because it's right now b float 16, which is this crazy numerical format. But we'd like to work with the standard float values, because the CPU is more used to this type of numerical representation. And then we sum the last hidden dimension, because the input embeddings, they have the format sequence length, batch size, right? Batch size, sequence length, and hidden dimension. And we sum over the hidden dimension to get this batch size and sequence length. And then we remove the batch dimension, which you can also do like this. And then we normalize it between -1 and 1. It's just for visualization, so don't worry. And that's it. So did everybody copy the stuff? Okay, so let's run it and hopefully it's correct. Can't call NumPy and tensor that request gradients. Aha. We have to detach. It's just how PyTorch works. If you want to convert it into a CPU tensor, also moving back from the GPU to the CPU, you have to detach it from the autogod graph. Okay, and it looks like this. Not really nice, isn't it? So you're actually correct. The gradient doesn't work. It's just, why does it not work? It's quite crazy. Actually, there's a reason behind this. In reality, the gradient is not just the signal of the model, but it's also overlaid by a noise component. Noise component. So here in the notebook, you have this demo. So we would assume the function of a neural network is quite smooth. It should look like this, and the gradient is also smooth. But in reality, it looks like this. There's a lot of gradient shattering happening, and then, of course, the gradient at these shattering steps are going crazy, and then the noise component is also quite high. And that's why you get these noisy gradients. For instance, here we have a text about medjool dates, some sort of fruit, in the Jordan Valley in Palestine. And then we explain the Jordan token, and it should highlight the Jordan token, right? Which is part of the input text, like the example before. And if you increase the noise level of the gradient, then the heat map completely breaks down. It doesn't work anymore. And that's why we have to use some way of denoising. And one of the problems, so you might wonder right now, why is the gradient even noisy? One troublemaker is, for instance, layer norm. Because layer norm, as you know, I hope you know, so it's just an operation inside these transformer models that rescales the input activations to stabilize the gradient. But what many don't know is that it also works on the gradients. So if you put in a small gradient, it will increase the gradient. And if you put in a high gradient, it will squeeze it down. It's just a way to stabilize the gradient over the training, so we don't get vanishing gradients or exploding gradients. There are also many other problems in transformers, unfortunately. So you have query keys interactions. You can just imagine you have keys multiplied together. And if you compute the gradient, it will flow through the query and through the keys. So it's basically doubling the gradient at each single layer, which might explode the gradient over time. Then again, at softmax value, it's all again exploding. And the zero nonlinearities again are distorting the gradients. So we have to account for all of these different effects. And that's why there's a technique called layer-wise relevance propagation. It works the following way, that you take the gradient of one of these troublemakers and you modify it in a way such that you denoise it, that this noise component is cancelled out. And the math is a little bit, it's not complicated, but it's too much for now. You can just read the paper, Attention LRP, for instance, where we go in detail and explain all of these effects and how you properly do a Taylor approximation so that it works. And the cool thing is, this technique I'm going to show you now is actually state of the art right now. So for instance, Anthropic, they had this amazing blog where they actually reinvented parts of LRP. OpenAI had recently another blog talking also about gradient-based methods, mentioning LRP. Then this Transluce startup, also everything from the US, was also using LRP. And then here's this nice paper from Jafari, Faithful and Efficient Circuit Discovery, where they show that LRP basically outperforms all other gradient-based methods. So this is actually cutting-edge stuff. Yeah?
Sorry, but they were much more than just again of nuclear. So was still possible to consider, for instance, you can part of encoders.
Yeah, this is something different. Because if you have these sparse autoencoders, you have to know which of these features are active right now. So use on top of this attribution method.
It's not part of the variables with which you will present.
No, it's explained in the paper also. They do a lot of different stuff.
Exactly. That's my point.
Yeah, I'm just telling that they're using it.
Right.
Okay, so let's do it very fast. So to do this, we need the LXT library. We monkey patch the model. So this means that we, in the runtime, we change the source code of the Hugging Face library. It's not so important how it works. We can talk about later on if we have time. So if we run this function, now the gradient is corrected. And now we can call our attribute input times gradient function again. We don't change anything. We have just monkey patched the gradient. That's it. And then if we do this, suddenly the gradient works again. So it highlights actually our correct token. However, here there's not much relevance, so it's not perfect yet, because it's still a approximation, right? It's not the original perturbation. Now, here below, we have a small Gradio demo. And it's important to know, so we have this prompt again, we compute the gradient as before. But now it's important to know that we can explain different token predictions, because the model does not only predict 182, it also predicts 27, right? And it also predicts a wrong number, 183. So we can explain each single token individually. If we explain, for instance, 27, we get this heat map. What happens if we explain this wrong token? Let's try it out. It's also looking at this one. However, interestingly, it's much weaker than the correct answer if you compare. All right, so this was just the prologue. Now the really interesting stuff starts. I hope you're still here. Everybody fine? Some questions? Okay, cool. Let's go. So now we just looked at some tokens in the input. Now let's start looking inside the model, some attention heads. So to get the attention weights after the softmax output, we can use again a function in the Hugging Face library. So you take this model and you just put in this flag, output attention equals true. Ah yeah. Cool. And then you retrieve the attention maps just by doing this, output times attention. Before we go on, I have a small exercise. Who can tell me the shape of this variable and how many attention heads we have in the model? You have 3 minutes, if you like. You can just copy this code above, maybe, and put in here the prompt and see what happens. Has anybody the solution? Yeah.
It says the double of attention tensors. It is helpful with 1 tensor per layer.
Yeah, it's 1 tensor per layer. How many layers?
It's tensor shape.
Can I answer?
Yeah.
16 layers.
Nice.
And 32 heads.
Per layer.
Per layer, yeah.
So in total, how many layers we have? Okay, I cannot compute it myself. So it's 512. So we have 512 attention heads right now. So here you can see, you just compute length. And if you wanna, so we have 60 layers. For each layer we have a tensor. And then we just take, for instance, the first tensor, compute the shape. And then we have 1, 32, 45, 45. This means the batch size is 1. We have 32 heads, and the sequence length is 45 times 45, because attention is always squared, right? This is our attention matrix. Now let's look at some attention maps in the model, just for fun. If you use VS Code, there's a bug that somehow it prints it several times. Should be now. When is it done? Okay. So when we look now at some of these attention maps, they seem to be, quite chaotic. It's quite hard to tell what's happening, right? You can play around if you like. Something's happening here. We have 512 attention heads. So it's just too much information, right? Maybe there's a way to cut it down. So we already know that in this heat map example, that only a small amount of tokens are actually relevant for the prediction of the model. So let's apply now this technique also in the latent space to cut out all of the noise and only find the attention heads which are really useful and responsible for the prediction of the model. So to do this, we have here this function, attribute attention heads. And what we do, we just retain the gradient on all of these tensors. It's just, again, a PyTorch autograd stuff. You have to retain the gradient if it's not a leaf tensor. If you don't know what a leaf tensor is, it's not so important. It just means it's not the input embedding or some input to the model. You just compute the gradient again on all of these attention maps, and that's it. So we just compute the gradient for each single attention map in the model. Are there any questions? So the main part is happening here. We take this attention tensor and we multiply it with its gradient, then we have the relevance. That's it. So after we've done this, so if you go back, here, back to these attentions, they have the following shape. We want to get rid of the sequence length because we want to have a single score per attention head. So what we do, we just sum over the last two dimensions so that we get a single score per attention head. We do it here. So we take now all these attention relevances, we sum over the last two dimensions, and we flatten everything. So this tensor has now the following shape, number of attention heads, okay, which is 512. Now we sort all of these attention heads and plot their relevance values. Then we get this. So on the x-axis you see the number, all of these attention heads, which are 512. And here you see the relevance value of each of these attention heads, sorted. And you see that almost all attention heads have 0 relevance. So it's quite sparse. Only approximately 10% of the heads are actually used by the model for the specific prediction, which also makes sense, right? If you think about a human brain, also not every single part of the brain is used, I mean, for vision or for linguistics, right? Everything does its own thing and is only active for specific tasks. So the key takeaway right now is that the relevance of attention heads is sparse. We do not have to look at all attention heads. Most stuff is just redundant and you can throw it away. It's not relevant for the prediction of the model. Are there any questions? Yeah. Also, microphone.
I'm sorry if you've mentioned this already, but could you maybe explain how this relates to in-context learning?
Are we getting to it?
Okay, thanks.
Yeah, because now we found out, okay, we do not have to look at all of these attention heads. So we can make our life easy by just looking at the positive ones, for instance, or the negative ones. But now we will focus on the positive ones because they're much more interesting. These are the ones helping to predict. The negative ones are the one suppressing the prediction. So we just ignore it for now and just focus on the positive ones. So 100 attention heads is still a lot, so let's just do some clustering and see what's happening. We take all of these attention weights, we cluster them.
So we take font size again.
Oh yeah.
Thank you.
Okay. So if you run the code, you should see this. Oh, it's gone. Okay, so in this code, we took all of these attention weights, their relevances, and then we just clustered it using UMap. Nothing special at all. And all of this code you can ignore. It's just some visualization stuff, which is irrelevant for us. And you get all of these clusters here. So if you like, you can take a look and see if there's some sort of pattern you can spot. Yeah.
Sorry, this is not really specific to LRP, right?
No, we use LRP to get all these relevances.
Oh,
so
okay.
If you go up again here, we computed the relevances for each single attention head for our Sahara Desert prompt, right? We did it via input times gradient.
Okay.
And we already used this monkey patching to change the gradient in such a way that it's denoising now. So it's working much, much better than before.
All right.
Okay. So you can click also on some of these dots, and then you get the attention maps or the attention relevances on top of these attention maps. And you see, for instance, the cluster here below. This one seems to focus on the correct answer token, right? And if you look at some other cluster, they're much more spread out. But the interesting thing is, these heads, they write into the last token position, because there our prediction is actually located, right? So they take some sort of information from the question and then write it into the last token position, because the flow in this attention map is always from right to left. So it's writing the keys here into the query here. So for instance, this other cluster seems to be focusing a lot on these question tokens, while the other one seemed to be focusing just on the answer token. So we see there is some sort of specialization happening. So let's just test it. So what do you think? How can we test now what each attention head is doing?
Exactly that we were doing.
He said, select, what did you say? Yeah, we can, for instance, shut down attention heads. That's a good point. Is there something else we could do? Yeah.
We could do make a synthetic data set where we create samples with a similar structure and then see whether we get this pattern.
It's also really a nice idea. Cool. Any more?
You have issues with the seek or potential that when its first position is not relevant, well, it's going to be it.
Yeah, there are actually some attention heads looking at the first token only. Let's see. Yeah, here, for instance, this one is just looking at the beginning of sequence token for some reason, and then writing its representation into the last token position. Cool. So what we can do, we can create a synthetic data set, we can deactivate the attention weights, but a much simpler way, which also works on a small notebook, is activation patching. So suppose we have this prompt again, and this is our model, right? Here's the end token of the question, and this is feeded into the model, and then outputted at the last token position. So we get 182, right? This is the prediction of the model. Now we have a second prompt talking about the Atlantic Ocean. So here it's saying it's the second largest ocean on Earth. It holds about 310 million cubic kilometers of water. And then it talks about the biomes. We have coral reefs and a lot of different stuff. And then the question is, which biomes does it support? So what will the model predict? Something about the coral reefs. It will say tropical coral reef systems. Is this clear? Okay, cool. So what we can do now, we can now identify a subset of heads. We can take their activations and patch them or replace them in another prompt to see what's happening. So we take the activations of these three attention heads at the last token position and then override it in a different prompt. And what will happen, maybe, so for instance, let's say these heads encode the question tokens or encode the task the model wants to perform. For instance, I have to find some sort of number about volumes or metrics. This might be some sort of vector or task in the model, in the latent space. Maybe it's encoded by these three attention heads. If we patch it now into another prompt, the model might say 310. It's not saying any more tropical coral reefs, but 310 million cubic kilometers of water. So we transferred the task of this model into another prompt. Okay. To do this, we have to replace the attention outputs. In Hugging Face, it's moduled in the following way. We have these basically 3 linear layers, and then at the end of the attention output, we have again a linear layer, which is the output projection. It's just the way the model is built up. And to get these attention outputs, we will apply a forward hook on this layer and catch all the inputs to this layer, which is the attention output. And if you're really interested in attention patching, I recommend this paper from Fred Zhang and Neil Nanda, Best Practices of Activation Patching. They will talk in detail about all different kinds of patching, what you can do, which baselines. So you can read it later on. For now, we make it very simple. So here we have our hook, which we apply on the output projection of the model. Maybe let's go to the main function first. So first we define, is everybody familiar with forward hooks in PyTorch? No? Okay, I think we don't have time to explain too much. It's basically, you define a function, which looks in this way. You put in the module, the input and the output, and this function is placed inside this PyTorch module, and it will get the input to this module and the output activation of the module. And then you can modify it inside this hook, and that's it. It's just some way to access the model from the inside. Just a PyTorch feature. So no worries, we don't have to go into detail. You just have to get the basic idea that we take these activations and patch them into another model or another prompt. So we do it, so we take the model, we take the SOM layer, and then we get into the self-attention layer, and then we get the output projection layer. There we register this forward hook that we define in the create hook function, which looks in the following way. We take the inputs, we reshape them a little bit to make the number of heads visible. I know this is a lot of code, and it's not so easy to understand. No worries, it's really not important. And then we replace the activation at the last token position. So let's just run the code. So what we do now, we have this Atlantic Ocean prompt. And now we got these 20 clusters from before. Right, we did this UMAP clustering, got all of these different clusters. Now we take the attention heads in each cluster, take the activations and patch it into this Atlantic Ocean prompt to see what's happening. Will it change the prediction or not? So if you run this, you see the baseline generation is tropical coral reef systems. And then the model will go on and talk about other stuff, because it's just doing next word prediction. So let's see what's happened. So if we take cluster 0, then we already see the prediction of the model has changed. Now it's not saying tropical coral reefs anymore, but 310 million cubic kilometers of water. So we were actually able to change the prediction of the model. But this does not always happen. So cluster 2, for instance. Let's go. Okay, does not let me scroll. Okay, I mean, we see it here. Cluster 14 doesn't change anything. I mean, it still talks about coral reefs. Here again, here again. That didn't change anything. But cluster 19 again changed it. So if you look through it, you just see a handful of clusters that did actually change the prediction. This one is also really interesting. So this one is just saying 18, 182 over and over again. But this one is not even in the prompt, right? If you go back to the original prompt, there is no 182 inside. Where might it come from? Yeah, from the left side. So this is kind of weird. This is some sort of attention head, which seems to have saved the correct answer of the original prompt, which is then transferred to the new prompt. Let's take a look at these attention heads. So what did we have here? We have cluster 19 is interesting. Cluster 12 is interesting. Cluster 6 is interesting. So let's see. Let's go back. So here, this is cluster 12, which changed the prediction to 182, 182. And we see that this cluster of attention heads was actually looking at the answer token. So this basically already proves that this attention head seems to be extracting the correct answer of the model, of the prompt. And another interesting cluster was this one. One moment. Which one was it? Yeah, so it's basically cluster 19, where there's a lot of relevance on these question tokens, which are then written into the last token position. So we identified two really interesting heads. One type of head seems to be inducing the task or the question the model wants to perform. And the other task of the other group of heads seems to be inducing the answer the model might give. And actually, it turns out that these heads also have a name. The one encoding for the task are just the task heads, or the basically function vector heads. And the tasks extracting the answer are retrieval heads, because they retrieve the correct answer token. And we can test this. So here's a function, get top k heads on substring. Because this clustering stuff was really tedious. We have to look at all of these clusters, and it's not so easy to do. What we can do instead, we can filter for heads looking at the question and filter for heads looking at the correct answer token. How can we do this? This function basically just takes the attention relevance from the attention map at the last token position, and then we put in the key indices of the query tokens, of the question tokens, or of the correct answer tokens. And then we sum it up, and that's it. Is this clear? Okay, it's not clear, right? Okay. Too much info. Okay, no worries. So remember, each attention map has this shape. And we computed the relevance on these attention maps. Okay. Now, we also know that information flows from the right to the left. So they get some sort of representations from the queries, from the keys, and write it into the queries. Okay? So what we can do, we can search for attention maps where there's a lot of relevance on the question tokens. And we can do this by basically summing up the relevance on these question tokens. And then we rank it up. That's it. If we do this, so here we see the top heads looking at the question, just some random heads, and here we see the relevance value. And we see the most important head has, I think, I don't know, 5 times more relevance than the least important head. So it seems that the relevance is dropping very fast, and these are the only heads really relevant for the specific task. And now we can patch it into the into our Atlantic Ocean prompt and see what's happening. So the normal prediction is tropical coral reef systems. Now we patch it again using our new set of heads we found, and it changes to 310 million cubic kilometers of water. So it seems to be working. The only thing we have to do, we just search for attention heads looking at the question. Very simple. And now we can do it also for other prompts. So we have this prompt, translation into German, I love AI research. And now we take all heads looking at translation into German. So these heads will encode the task, translation into German, and then we can prompt it, patch it into other prompts. So we have this prompt, write the opposite of the sentence, the car is going very fast. Let's just prompt in the German feature and see what happens. So the model is saying the car is going very slow. This is the normal prediction. And now with the patch one, der Auto, that's not really good in German, ist sehr schnell. So you see, it's not perfect, right? But there seems to be some signal. Are there any questions?
Yeah. How would you do it if the half is not a subsequent? And all in the beginning is like something and blah blah blah.
Yeah.
By the way, and also this.
That's a good point. So in this case, the code doesn't work because we search for a substring. So usually what I have observed, that the model is taking this entire sequence and writing the final representation into the last token of the instruction. So it seems to be merging everything always into the last token. Cool. If you like, you can play around with different prompts. Or take a small break.
Patching. Is this patching sort of similar or equivalent or something like that? There used to be this thing before the current AIs where you take a picture or a text and you ask it to do it in the style of artist X or writer Y. Would it be a similar sort of transformation, or is it just a coincidence that?
No, that's actually a good point. So if you have this type of prompt, I mean, it's also language models, right? You can type in some task and then the model performs it. What's happening is that the model is taking all these task tokens and compressing it into some sort of activations which represent this task. So we just skipped this entire process and just took directly the activations. So it's actually similar. It will end up the same way, except this is a little bit not really robust. Exactly, yeah.
Is this a property of all LLMs that certain heads encode for the task, or is it just a property of Llama?
We will touch on it later on, but I will spoiler, it's actually universally above all language models.
Oh, wow, interesting. So irrespective of the training algorithm, it's a property of all LLMs.
Completely independent, whatever you want. And we'll see also why it happens. But regarding training algorithm, I'm not sure, because right now you do this next token prediction or mask token prediction. If you do classification, for instance, it might not be the same.
As a theoretical question, couldn't this sort of technique be used to patch models to give different answers if you want to censor or change information or change history sort of thing?
Yeah.
Okay.
So there is a line of work which is doing prompt compression. So usually you might have 10,000 tokens instruction prompts. Have you seen it where people leaked the instructions of ChatGPT? Right, that I don't know, 50,000 tokens. You can actually compress it quite smartly into just 5 tokens or 5 activation vectors. And then you save a lot of compute. Or you can enforce that the model is always performing the task. Because sometimes the model just diverges, does different stuff. And you can correct it again by injecting this activation vector, telling it, no, do this task now. So, yeah.
There is one more question. I have a question regarding the examples at the beginning where we highlighted the prompt, like input prompt. So, for example, in computer vision, it makes sense because we have an input and we want to see the predictions in the input on the image. But how do you think is it useful for language models? Because usually we can ask anything without giving the answer in the prompt, and the model looks in the internal kind of database. So how is it useful, or is it useful at all?
That's a very good point. So the problem with language models is that they hallucinate. So you might ask, where did you get this information from? And it can just make up something. So that you have no guarantee whatsoever. However, with the heat map, you are 100% certain where this information is coming from.
Actually, I'm not sure, because it can hallucinate, but you cannot see the internal kind of information, Like you cannot identify source just by highlighting the input prompt. The source of the hallucination, or from what source this information comes, this hallucinated one.
I mean, so in our example, if you compute a heat map, we saw where the source was, right? But your question is if we can find the source if it's hallucinating, or?
I mean, if it's useful to use heat maps.
Yeah.
Because, for example, the model can say the president of the United States is, I don't know, Angela Merkel.
Okay.
But you don't have it in your prompt. It is in the dataset.
Yeah, this is something else. So it only works if it's in the context. So if you do, for instance, deep research with ChatGPT, it's collecting a lot of different news articles and synthesizing everything. There it could be really useful, because then you get actually correct citations, or if it's scraping the internet, right? But if it's just talking from its own memory, then of course input heat maps will not work. However, something else will work, because we can also trace the latent state of the model, and we can also find the neurons which were responsible for the prediction. So, like you said before, we can use SAEs. I'm not sure if you are familiar with them. It's just some sort of autoencoder which allows us to get interpretable features in the latent space. And then we can also compute relevances for these autoencoders and see which parts of the model contain this information and also what this information is. So what will happen is, in your example, the president of the United States is Angela Merkel. We will see that at the president position token, there will be some MLP block that contains a neuron responsible for Angela Merkel, which is directly connected to President of the US. So it's just a matrix where you put in President USA and it puts out Angela Merkel, like a key and query. This is just how an MLP block works in general. It's just, right, you have this X, matrix multiplication, you get Y, and this Y contains then the answer to the question. And this is happening inside each MLP block in the model. And you would get these blocks. And you would find out which exact and which neuron exactly.
How did that fix it?
Yeah, of course, yeah. That's a good point. If you know where it is, yeah.
I think a use case is also for RAGs, I think. In industry, you would use this for RAG, and then you know whether your model references something that you retrieve. And then
that's a good point.
That's for hallucination.
Actually, we will do it later on. We will use this technique to see if the model did actually retrieve RAG context or if it just made up information by looking into its parameters. Right? It could be that there's some news article which is outdated. For instance, one funny phenomenon was this Venezuela attack. If you ask ChatGPT, it would say this is fake news. It doesn't. It's completely improbable. It actually works. You can try it out. I don't know if it's patched already, but we can spot this and say, oh, okay, the model doesn't believe this because of Y, Z, Z, and so on. Yeah.
I guess we kind of saw the hallucination when you were showing the Gradio example, right? So there was 182, 27, and 183, right?
Ah, true.
And then, like,
it was a little bit less relevant on the 182, right?
So probably there's a neuron which was taking 182 and then adding some number to that, right?
Exactly. Yeah. Perfect. So you would see in the latent space that there's some relevance flowing in some LMP block, which is not present for the correct answer. That's a good point. Okay. Cool. Any more questions? Can we maybe open the window or something? I mean, just if you like. Okay, cool. I mean, it's really cold. Just keep it close there. Sorry. Okay. We can do the same experiments now with retrieval heads, but I think it's kind of not so. It's kind of boring because we have other stuff to do. So let's now go into your question about parametric knowledge. So the goal now is we found these. That's one thing I've forgotten. I'd like to show you where these task heads and retrieval heads are located. Okay. So the interesting thing here is we got these heads from translation into German, and we got heads for how much dust is blown into the Sahara. And if we plot this, we see most of these heads are located in the middle layers. Just some smaller outliers in the earlier layers. And if we plot now this retrieval heads, which retrieve the answer, they're located at later layers. This is important to remember later on. So now we try to find now the parametric heads. Where does the model store its internal knowledge, right? So to do this, we use contrastive explanations on counterfactuals. So we have a prompt. The capital of France is London, which is wrong, right? Now we ask the model, what is the capital of France? Now it will have two predictions, either London or Paris. Now we can explain each token separately. We can explain the London token and find all attention heads responsible for encoding London. We can do the same for Paris. We can find all the heads encoding Paris. The difference here is London is coming from the context, from the reg system, right? Paris is coming from the internal parameters. It's not given in the context. But you see, some heads are active in both cases. But we just want to find these heads which are individually for one case. What we can do, we just subtract both relevance flows. We take a smaller, a bigger data set, you compute the mean, and on average it should cancel out. Just an approximation. And then we get all of these parametric heads and all of these contextual heads. Are there any questions?
Sorry, could you repeat? Could you just repeat?
Any questions?
Could you just repeat what you just said about...
Okay. Everything or? Okay, very fast. So we get now two token predictions, London and Paris. We explain London to get all heads responsible for London. Then we explain Paris to get all heads responsible for Paris. But some heads will be used in both cases. We want to cancel out these heads because they're neither parametric nor contextual. So we subtract everything and that's it. Cool.
One question.
Yeah.
Like when you do the uplift as well.
We can subtract either way, yeah.
Well, you could be interested in what's common.
Yeah, good point. Yeah, true. Really interesting, yeah. So I've defined a lot of prompts here. Like this Paris London example. The iPhone is made by Samsung. Some people might be not happy now, but that's okay. Tesla, Elon Musk, colors, I don't know. And this is just a helper function we can ignore for now. And what we do, we do a model inference. We take the top k token predictions. Now our helper function is checking if the parametric answer is present or not, or if the contextual answer is present or not. Because we defined here, parametric answer is dog here, context answer is cat, and the question is what animal barks. And then, if the parametric answer is available in the top k tokens, we explain it. We compute again the relevance on all attention heads, and we save it. We do the same for the context prediction. So let's run it. We are done. And let's just do clustering with PCA. We have all of these relevances on the context, all relevances on the for the parametric prediction. Let's just see if there's any signal, anything we can see. It will look like this. So we see that if we explain the context, there seems to be some different representation of the relevances. In contrast, if we explain the parametric answer, it's not perfect, but there seems to be some sort of signal, right? So let's do this now. We do this contrastive explanation. So this line is important here. We take now the mean of the parametric relevance. We take the mean of the contextual relevance. And then we subtract it. That's it. So if we have a positive score, what does it mean?
That's the answer.
Doubling the answer.
Which answer? From parametric knowledge. And if it's negative? Exactly. Are there any questions on this? Okay. So let's just plot this diff variable, right? Which size does it have? Yeah, so number of heads. 512. We get for each single head a single value. Once for parametric case, once for contextual case. And we subtract this. Okay. So it looks like this. So we see most heads are 0. It seems to be working. And approximately 25 heads have a high difference value, which means what?
1. There must be parameters. I was become lost in knowledge.
Exactly, they're parametric. And many have, I mean, also 25 have negative values, which means they are contextual. So now let's take these heads. And plot them inside the atlas. I mean, we just plot their position over the model. So we see here the layers of the model. This is the beginning of the model. This is the end of the model. And then all head IDs. What do we see? Is there some surprising trend?
How that's the proper.
Yeah, exactly.
Certain ends are more about the context of the parallels. Through these used to detect prompting text effect, where we would know where the user came from if it was injected by the user or by the source. So when you submit a CV or in a web page, and the AI reads the instruction there to alter the purpose behavior, would this be detected by seeing that the answer came from the context and not from its knowledge?
I think in this case, the model is using the context, right, to do this adversarial task. So the context heads would be highly active. However, there are many works on adversarial example detection and anomaly detection. I think also a colleague of mine has worked on this and has used relevances to do anomaly detection. And he found out that in these cases, the relevance is unusual. So it's still on these context heads, but it's not normally distributed. So this is maybe how you can use it. Okay, cool. So you see here, in the first layers, we have almost exclusively just parametric heads and some smaller outliers, right? And in the middle layers, or to the end, we have a lot of in-context heads. And this is not random. Actually, if you do it, one moment, this is coming. So, if you do it on much larger models and with much more data, you will get this map. And the funny thing is, how many layers does our model have again? 16. And this one has 32. 16 ends exactly here. Right? So this looks like our plot from before. But now, if the model is getting bigger, it's the same llama model, just more parameters. Suddenly, it fills up with parametric heads. Yeah.
Ist so feststellen, is the shorter llama model so serving as a pre-trained seed for the bigger one?
No.
Okay.
It's maybe the opposite. They distilled it from the bigger one.
Ah, okay. So that's because the
good point.
matches, right?
Yeah. Good point, yeah.
The models have a higher chance of
I would interpret it differently, that bigger models just have more knowledge. That's why they fill up everything they have with parametric heads. And interestingly, their contextual capability seems not to be increasing. I don't know, I'm just doing now the hypothesis, just looking at the atlas. We have to do some rigorous analysis, but it seems to be the case. Right? And this structure also makes sense, because in the earlier layers, we have these parametric heads, which just inject some semantic knowledge about the tokens. Then in the middle layers, the contextualization happens. The model is trying to connect different tokens, tries to understand the question. Here in dark blue, we have the task heads. They're also in the middle. And now, if we go down, the model already knows which task to perform. Now, the answer retrieval happens. So the green heads, these are the retrieval heads. These crazy heads that always extract the answer token, which happens at the end, which also makes sense. So it's a 3-step process. First, enriching the prompt. Second, understanding the prompt or contextualizing. The third step, extracting the answer. And you can actually see it inside this atlas map. So I have to share again. No worries.
So again, if you were doing something like a RAG, retrieval, or task, don't you think that this will increase the chance of having a hallucination if you have a bigger model?
Generally, what we observe, just from benchmarking models, the bigger the model, the less hallucinations. It also depends on the training regime. So it's not a yes or no answer.
Even if it were only for learning?
I don't know. I don't think so. So I think the model size correlates negatively with the hallucination rate. So the interesting thing is, for instance, open AI models, they have the least, Claude models from Anthropic, they have the least amount of hallucinations right now. That's why they're so perfectly used for programming, right? Because if there's one column not correctly set, then everything breaks down. So somehow this pre-training on a lot of code seems to help against hallucination. I don't know what they actually do in their labs. And the Gemini models, while they outperform really nicely, there was a lot of hype, they actually have the highest hallucination rate. Yeah. So they seem to, I don't know what they actually do in the lab, so we can just speculate. But Sam Altman says he has some special training recipe which he uses to decrease hallucination. So I assume they just have some synthetic data set where they actually train the model to say, I don't know, if it doesn't know. So it doesn't hallucinate. But you can never turn this off. It's actually a feature. Hallucination is a feature of models. Just the way it's trained, it has to predict something, right? That's why we need explainability to maybe prevent this type of stuff happening. So how much time is left? 4 minutes? Oh. Okay. Okay, let's do one last thing, because we want to eat pizza, right? So let's build a small monitoring system. Let's go into the practice. So what we do now is, we found all of these parametric heads, and we found all of these contextual heads. Now, if the model is predicting a token, let's see if it's actually coming from the context, or if it's coming from the internal knowledge of the model. So we can actually judge if it's maybe hallucinating, if it's giving its own opinion, or if it's actually grounding its prediction in a RAG system. To do this, you don't have to understand this code in every single detail. Basically what we do, we take our parametric relevances, our contextual relevances in the first 2 lines, and we select only our parametric and contextual heads. We got 25 parametric heads, 25 contextual heads. We concatenate these IDs, and we select the relevances. That's it. We just take the relevances of these heads. Now we train a classifier, a linear classifier. It's just a linear discriminant analysis. You can take any classifier. This one is just really fast. And then we compute the accuracy of the model of this classifier using leave one out accuracies. And we see we got 100% accuracy on this small test set. It's just 24 samples, so nothing special. Now, we have this prompt. Assume there is a physician who has a patient record. So it's about John Smith. He has some chest pain and shortness of breath. Now we tell the model, you are a medical assistant. Give the physician a small summary and some recommendation what he could do. So let's see what happens. This will take a lot of time because I'm just using my Mac Pro. So I don't know how long it will take. So just drink something or relax.
This creator is looking at which heads are being activated in what generations or how is it estimated?
Okay, so the model is doing a prediction. Some token. Now we explain this predicted token and get the relevance on the attention heads.
Yes.
Then the classifier will see if the relevance is mostly on parametric heads or on contextual heads.
Yeah.
Okay, we got some generated text. And now, no, it's still takes time, okay. 3 minutes. Okay, are there any questions in the meantime? Yeah.
Can you just say again just what question is? Explain it.
Okay, cool. Okay, so we have this model, which has this patient record. Now it generated this text, handover summary John Smith, just reiterating what it saw. And then later on you will see it gives some recommendations how to treat this patient. Now we take each single predicted token, we may make one backward pass. So, right, we have one forward pass, one backward pass. We take all the gradients on these attention heads, multiply the activations of the attention heads with the gradients, input times gradient, right? The Taylor approximation, which we denoise with LRP. Then we get the relevance on these attention heads. We sum over the sequence token dimension so that we get a single scalar value per attention head. You know, this attention map is 2D, so we have to make it 1D by summing up everything. This way we get a 512 large vector. Because why? We have 512 attention heads. So now we have this vector which represents the internal state of the model. How much is each attention head active right now for this specific prediction of the model? Now we train a classifier to look at this 512 long vector to discriminate if it's mostly parametric or mostly contextual. Okay, cool.
You maybe show the map again, and maybe you have this one for this.
Yeah.
Especially what I missed is some dogs that are bigger, some are smaller. What does the size mean?
Yeah, good point. In this figure, everything has the same size, right? But in the Jupyter notebook, the size of the dot signifies its relevance value.
Ah, but so higher one.
Exactly.
Okay. I know one heads which belong in the dog, they're like not used at all, right?
Exactly. I mean, they're not parametric. They are neither parametric nor contextual, which is just the opposite, right?
So what is it that if you're not contextual, not parametric?
They're used in both cases. Exactly. Yeah.
Thank you. So we saw this, especially in a very small context in this case, because we're using a small model, we're using very few prompts.
Yes.
How stable is this distinction between, actually in the other paper you showed 4 different tasks for the various heads.
Yes.
How stable is this distinction when you're working on larger models and much bigger prompts, especially with, I'm guessing, cases where you don't have this kind of almost prompt injection where I'm almost playing with the model and telling it, oh no, Paris is the capital of the England. So this is very stable and becomes stabler with larger models, or do they become a bit less stable?
Exactly. So we did it on many different models. For instance, Llama models. For Meta, Mistral models from Mistral, the Google models, the Gamma models, and so on, and on different sizes. And this is actually a universal map. It just holds true for all of these models we have tried out. And in our cases, we also tried small prompts, also bigger prompts, 10,000, 50,000 token length. We did not go beyond this token length, but I assume it will stay the same. So we already saw for this small prompt it works. It also works for these 50,000 token prompts. So it's quite stable actually. And we did it also not on these smaller prompts, but actually we used real-world data sets like natural questions, trivia, QA, and all of the stuff. So it's actually questions people ask in Google and so on. So really diverse, a lot of different questions, everything you can imagine. Yeah.
Do you have a hypothesis for the reason behind this behavior?
Sorry?
Do you have a hypothesis about why this is the case, that all models have this pattern?
Actually, I don't know. It seems to be that gradient descent converges to this, using this architecture and training on the entire internet. But it makes sense, right? At the beginning, you enrich the prompt with some background knowledge. Then you try to figure out the task you want to perform. And after you found out what to do, you just activate all heads to perform this. So we found, for instance, specific heads, which we call the copy controller heads, that control these retrieval heads what to copy. So it's quite funny. They write some identifier in the residual stream. It's like a pointer in C++. And then these retrieval heads read in this pointer, and then they copy the token. So there's a lot of stuff happening in these middle layers. But it's basically an ocean, right? There's so much stuff happening. We still do not know so much. So basically, like a neuroscientist, we know, okay, this part of the brain is doing this and this, but we still don't know how the brain actually works in detail, right? So we actually have the same state right now in language models. So if you're interested in explainability, there's still a lot of stuff to do. And you can publish a lot of papers, do research in this area. It's basically just it's an explosion happening right now.
One more follow-up question to that. In the other plot we saw for a larger model, we saw that the number of heads responsible for prompt enriching do not increase.
Sorry?
For the larger model, we saw that the number of heads responsible for enriching the prompt, they don't really increase, right?
Yeah, this is quite interesting.
But how would you explain that? Why?
I think if you make the model bigger, it just uses its parameters to memorize more stuff. But I don't know why it happens. Maybe because we know that large language models, they suffer from the loss in the middle effect. Which means if you have a really big prompt, the model just gets lost. It doesn't know where to look at. And this might be explained by the fact that its contextual capabilities do not scale with the parameter size. So you might need some extra training to encourage the model to create more contextual heads. And this might fix the problem. But this is just a hypothesis from my side. Yeah.
Thank you. Very interesting workshop, by the way. I had a question about the universal atlas you showed, because I assume you did the monkey patch and LRP beforehand as well. How would that look differently if you would not reduce the noise for the gradients in that?
I haven't tried this out yet. I don't know. Yeah.
Okay, because I was wondering if you have like a less clear separation between in context and parametric parts and relevances.
So what we tested, we compared it just looking at the activations, right? You can just look at the attention maps, don't use any relevances, and just sum up the activations. But we found out that this doesn't work at all. So you wouldn't get this nice map because activation does not mean that this head is actually relevant for the prediction. Just imagine this prompt again with the NASA satellite. You have a lot of activation on the NASA token, right? But it's not relevant for the prediction of the model. So there's a big distinction between relevance and activation. And I think if you use gradient times input without LRP, if you do it over a huge data set and you take the mean, it might be that this averaging operation is like a low pass filtering. So it could be that it denoises it helps in denoising. Right?
Okay.
So it's like in signal theory, where you use low-pass filters by averaging.
So in the end, you would end up with the same map.
I don't know. It just might be not so obvious, the difference.
Yeah, no, makes sense. Thank you.
Cool. Yeah, so okay, let's look what the model did. Okay, no, one question.
Would that mean the remark that you just made that LRP is superior to all other methods, or what do you think about that?
It depends on your use case.
All right.
So for, let's say this averaging effect does actually denoise, I don't know, then you don't need LRP. But the cool thing is, it's for free. This monkey patching does not affect your efficiency at all. Why not just denoise the grading from the beginning?
Yeah. Well, there's a follow-up question. LRP is XAI somehow, and
it's a method. So XAI is a broad. Yeah, there's a lot of different stuff.
Right. So XAI is a kind of top church.
Yeah.
But it's kind of different community from mechanistic interpretability.
Not really. So.
Not really. Okay.
So yeah. So originally, before the transformer hype, there were still neural networks, right? Like convolution networks and all of the stuff. And when people started to explain all of these standard models, they called themselves they called this field explainable AI, because you're trying to explain it. Then other people said, no, don't say explainable, name it interpretable AI. And all the other ones said credible AI and all of the stuff. So the naming is not so important. But then ChatGPT came into existence. And now everybody was hyped about, okay, we have to understand these models, otherwise we will all die, right? So what they've done, a lot of new research labs came into existence. And there was one famous guy called Chris Olah. And he's a legend. He's really nice. You have to see his work. And he's also a pioneer in this field. And he said, I want to understand neural networks just looking at the weights of the neurons. I want to go really, really, really deep. And he actually has some works. It's called circuits. You can just type thread circuits, Chris Olah, and so on, where he analyzed single convolutional kernels. So he actually looked at these kernels and tried to understand what's happening there. So deep, you cannot go deeper, right? It's like reverse engineering assembly code. It's just crazy. And this is where he said, I call this type of research mechanistic interpretability. Because I'm like a mechatronic guy, right? What happened then is people figured out, oh, it's not so efficient. You cannot look at all rays of the model. It's just too much. Let's use again gradients. Let's use again perturbations. Let's use all of the stuff again. And then it just merged back, and people kept the name mechanistic interpretability, but now it converged back to the stuff people did before. So it's just naming convention.
Yeah, sure, but there are courses somehow, like the arena courses, and it would be cool if LRP would be included into there, so that one had the context in which it's most relevant actually to use actually, the method, right?
So, actually, that's a good point. Yeah. So if you go into the slides, here, I cannot share. Okay, let's share. Another really famous guy in this mechanistic interpretability field. Oh, you cannot see it. Okay. I can just Google the paper. Is it back? Ah, no, it's okay. Oh yeah, okay. I don't know if you see it here. That's Neil Nanda. He's really famous in this field. And they just published some months ago that LRP is superior. So, Okay, that's cool. So the field starts now to acknowledge it. This is what I meant, that Anthropic, OpenAI, Transluce, all of these startups now start to use it. Yeah, it's approximately just 6 months ago, 1 year ago. But LRP is 10 years old. And the inventor sits there. So he's quite famous, actually. Yeah. Sebastian Pushkin.
I have a couple questions, maybe. First, you say state of the art, but how do we actually measure? You know how good the method is.
Good point.
You know,
So,
compare. Yeah.
There are different ways. One way, what they've done in this paper, they've looked how well can we extract circuits from the model. So what are circuits? Circuits are actually subgraphs. So you have, again, this model architecture, and then you want to get a subgraph which explains a specific behavior. So let's say you want to understand how does the model perform addition or subtraction. You put in a synthetic data set, and then you prune the model. So you do relevance analysis, get all the relevant heads, and you take out all other heads which are irrelevant. And then you prune it down. And then you measure which method has the highest pruning rate. Because the better the method, the more heads it should identify which are correct and kick out irrelevant heads. However, if it's noisy, it will not have a nice pruning rate.
I mean, it's a trade-off between pruning rate and accuracy, I guess. No, because otherwise you can prune everything, right?
Yeah, you might get some curve.
Yeah.
And it's maybe like F1 score or something like this.
I see.
And then you can see which method has the highest score.
I see. And so I guess that brings me to my follow-up question. That was like, yeah, has this been tested for pruning, or how good is it? And then I guess it's SOTA for pruning.
It's done for circuit discovery, yeah, for pruning, yeah.
Okay. And has it been used for data filtering, for like model pre-training? And then you can maybe look at, you can explain which pieces of data activate and help to learn, and then and which are bad also.
Yeah, Sebastian might have an answer. It's good.
Is known as feature attribution. It means we explain what the model is doing in terms of, or we identify the important stuff in terms of features, which means here tokens, images, only pixels, and so on. What you're referring to is data attribution. It means we explain what the model is doing, and we try to identify what are the impactful data points which affect either this particular prediction or the model in general. We have published a recent paper which is called, change the title, therefore I don't know it. The method is called dual XDA. And this is a data attribution method inspired by LRP. And it works in a similar way, which is millions of times faster than the state of the art. Therefore, you can actually use it now for doing stuff like causal selection, which means from a huge data set, and you have a small initial model, figure out which data points are the ones which are really select those, and just keep in the model and others.
I see. Cool. So this has already been tested, I guess, on LLMs, or like has it been done large scale?
We have a showcase on the on LLMs compared to other methods. But this is not the focus of the paper. The follow-up.
I see. Okay, cool.
Because previously, the whole set of data methods, they usually play around with MNIST and maybe image that like, and there is a modify. Because the workflow depend on the schedule or autonomical model will take weeks. Correct.
I see. Okay, very cool. Thanks. Yeah, I guess that was it from my end.
Okay, let's go to the grand final. It's finished. Let's see what happened. So this is the original patient record we gave the model, right? Remember, it has to give its opinion on this patient for a physician. Now it generated a text, we see here below. And a red color means this token is coming from its parameters. A blue token means it's coming from the context, from the contextual heads. And we see here, for instance, it starts with patient information. Name, John Smith. Name is interestingly parametric, right? If we go back to the patient record, we don't see the mentioning of a name at all. I mean, of the name token. It just says John Smith. So the model just said from its own memory, name, name John Smith. Woo. Okay. Cool. So now it says, okay, it's just giving all of this information. It says in the context, which makes sense. And now it says the patient reports chest pain, shortness of breath, which is all in the context. Which, again, this is from the parameters, started 3 hours ago. This part is actually in the context, but which, of course, not. And now, if you go on to the right, we see, given the patient's history of hypertension, the current medication, so this is yellow because this means it's partially parametric and partially contextual. So you can even say this. It's essential to consider cardiac involvement. So this one is 100% parametric. The model is just giving its opinion. It's not in the patient record, right? Which I think is quite cool. And then again here, it's just giving some recommendations, everything red, except if it's citing some state of the patient, like its BP, which is the heart rate, or the chest pain, and so on. Yes. That's it basically for today. Thank you for joining this workshop. It was really cool, really nice. Actually, my first one. I hope it was okay. Thank you. And remember, this field is really young. There's a lot of stuff to discover, and it's just the beginning. And I would invite you to do research in this area. It's really exciting. And also, if you're a student, you can apply as a HIVI, if you like, at HHI Fraunhofer. I think they always search for students in this area. Okay, cool, thanks.